26,000 light-years from where you sit, our galaxy's heart beats in violent bursts. James Webb aimed its mirror at the Milky Way's core. What it captured terrifies astronomers. The telescope revealed needle-like structures piercing through space, defying every explanation. 500,000 stars scream in regions so dense that light itself gets trapped. Massive infant stars 30 times bigger than anything we've seen are forming in darkness. If you're curious about what lurks at our galaxy's center, hit that like button and subscribe for more. Prepare yourselves. We begin. James Webb launched on Christmas Day in 2021. Scientists expected discoveries. They got a revolution. Within months of activation, the telescope aimed its mirror at the early universe. What appeared on the screens made veteran astronomers question their entire careers. Galaxies swarmed across images of cosmic dawn. Big galaxies, bright galaxies, galaxies that had no business existing when the universe was barely born. The predictions said small and dim. Reality delivered massive and brilliant. Every theory about galaxy formation assumed a slow process. First, tiny clumps of stars would gather. Over billions of years, these dwarfs would smash together. Eventually, after countless mergers, galaxies like our own would emerge. The math worked perfectly. The timeline made sense. Everything fit. James Webb looked back 13 billion years and found the timeline was fiction. Massive galaxies already lived and thrived when the cosmos was only 500 million years old. That's 3% of the universe's current age. Imagine a human baby born with a PhD and a mortgage. The comparison barely captures how wrong this feels to physics. Joel Leha studies galaxies at Penn State. When he analyzed the first images, his words were blunt. It calls the whole picture of early galaxy formation into question. This wasn't minor confusion. The foundation shook. The telescope operates in infrared. Human eyes see visible light. Webb sees heat. This matters because ancient light stretches during its billion-year journey to Earth. What started as visible light arrives as infrared. The farther away something sits, the more its light stretches. Webb was designed to catch these ancient photons, and catch them it did. Thousands of data points flooded in. Each one confirmed the impossible. Galaxies filled the infant universe, like cities fill modern Earth. Dense, organized, mature. The cosmic nursery looked more like a cosmic metropolis. Scientists checked the instruments. Calibration errors could explain strange readings. They recalibrated, ran diagnostics, checked again. The readings stayed consistent. The galaxies remained impossible. Some tried alternate explanations. Perhaps these weren't galaxies at all. Maybe something else masqueraded as mature stellar cities. That hope lasted until spectroscopy arrived. Breaking light into its component wavelengths reveals an object's true nature. The spectra confirmed it. These were real galaxies, ancient, massive, impossible. The implications spread through astronomy like cracks through ice. If galaxies assembled this fast in the early universe, our models of cosmic evolution were fundamentally broken. If stars formed at rates 20 times faster than modern theory allows, we misunderstood star birth itself. If dark matter couldn't explain these structures, we might be wrong about the invisible scaffolding holding reality together. James Webb kept watching. Each observation brought more confusion, more impossibilities, more terror for scientists who built careers on theories now crumbling. And the telescope was just getting started. Our galaxy has a heart. That heart is a monster. Sagittarius A star sits 26,000 light-years from Earth, a supermassive black hole, 4 million times the mass of our star, 14.6 million miles wide, a tear in space-time that bends reality around itself. For decades, astronomers glimpsed this beast in fragments. Ground telescopes struggled through Earth's atmosphere. Space telescopes grabbed brief snapshots. Everyone knew Sagittarius A star was active. Nobody knew how active. James Webb pointed its infrared camera at the galactic center in 2023. The telescope watched for 48 hours straight, 8 to 10-hour blocks, multiple sessions across a full year. The longest, most detailed observation of our galaxy's core ever attempted. What the data revealed shocked the research team. Farhad Yousefzadeh leads the Northwestern University team studying these observations. His description was immediate. It is always bubbling with activity and never seems to reach a steady state. The black hole throws a non-stop light show, flickers, flares, eruptions, constant chaos. The activity operates on multiple timescales. Short bursts last mere seconds, faint whispers of energy that bloom and fade before you could blink. Medium flares rage for hours. Blinding eruptions that pump out more energy than our entire star produces in days. Long oscillations stretch across months. Background variations that surge and fall in slow cosmic breathing. 5 to 6 major flares erupt every single day. Between these monsters, smaller subflares pepper the accretion disk. Gas and dust swirl around the black hole at speeds approaching light. This swirling creates friction. Friction creates heat. Heat creates radiation. The whole system glows like a cosmic bonfire. Previous observations missed most of this. Ground telescopes could only watch for a few hours at a time. Atmospheric interference scrambled the signal. Earlier space telescopes lacked sensitivity. They caught the occasional bright flare but missed the constant background chaos. James Webb's infrared vision cuts through cosmic dust. Its sensitivity picks up even faint variations. The full picture finally emerged, and it's terrifying. The researchers expected some activity. All supermassive black holes flare occasionally. Matter falling inward releases energy. Magnetic field lines snap and reconnect. These processes happen everywhere. But Sagittarius A star never rests. The team watched it across multiple observation sessions. Every single time, the black hole was active. Never calm, never steady, always churning. Howard Bushouse studies these observations at the Space Telescope Science Institute. He compared the disk activity to solar flares. Blobs of gas are bumping into one another, and in some cases being forced or compressed together by the strong magnetic fields. Imagine a trillion-ton car crash happening every few seconds. Now imagine it never stopping. The small flares probably come from plasma fluctuations. The swirling gas compresses randomly. These compressions release temporary bursts of radiation, quick flickers in the darkness. The large flares tell a different story. Magnetic field lines within the disk clash and reconnect. This releases stored energy as particles. These particles accelerate to nearly the speed of light. They shoot away from the disk as blazing jets. Our galaxy's heart never sleeps. It feeds constantly, screams endlessly, and James Webb captured every moment in unprecedented detail. 300 light-years from Sagittarius A star, something strange pierces the cosmic fog. The region is called Sagittarius C, a star-forming zone near the galactic center. James Webb aimed its near-infrared camera at this patch of space. The resulting image shows approximately 500,000 stars. Protostars glow like bonfires. Dust clouds block background light, standard stellar nursery activity. Then astronomers noticed the needles, thin structures cut through the ionized hydrogen, bright cyan in the processed images, sharp, distinct, dozens of them scattered across the region. Each one stretches for light years. They point in random directions. No pattern, no organization, no explanation. Samuel Crowe investigates this region. An undergraduate student at the University of Virginia, he serves as principal investigator for these observations. His assessment was direct. There's never been any infrared data on this region with the level of resolution and sensitivity we get with Webb, so we are seeing lots of features here for the first time. The needles appear to be jets or outflows. When young stars form, they often shoot material perpendicular to their rotation. These jets clear away surrounding gas. The process helps stars shed angular momentum. It happens throughout the galaxy. Astronomers understand the mechanism, but these needles refuse to follow the rules. Standard stellar jets align with magnetic fields. The galactic center has powerful magnetic fields threading through it. These fields should organize the jets, make them point similar directions, create some structure, some pattern. The needles ignore this completely. Each needle points wherever it wants, up, down, sideways, diagonal, as if the magnetic fields don't exist, as if each young star operates in total isolation from its cosmic environment. The region also shows massive ionized hydrogen emission. Energetic photons from young stars strip electrons from hydrogen atoms. This creates glowing clouds. The process is well understood. What's not understood is the scale. The emission extends far beyond what the visible stars should produce. Either there are hidden stars pumping out extra energy, or something else is ionizing the hydrogen. At the heart of one cluster sits a protostar, still forming, still gathering mass, already 30 times as massive as our star. This infant will become a true monster when it finishes growing. For now, it huddles in darkness so dense that background starlight cannot penetrate. The cloud appears as a hole in the image, a void where light goes to die. Smaller infrared dark clouds dot the entire region. These are future stellar nurseries, places where the next generation of stars will ignite. The galactic center breeds stars faster than almost anywhere else in our galaxy. The density helps. Gravity works overtime. Gas compresses quickly. Stars form rapidly. The environment is chaos. Intense radiation, powerful gravity, crushing magnetic fields, stellar winds, supernova shockwaves. Everything that can disturb star formation happens here simultaneously. Yet, stars keep forming, keep growing, keep defying the hostile conditions. The needles remain unexplained. Astronomers study the data, run simulations, test hypotheses. Nothing fits. The structures shouldn't form this way, shouldn't point these directions, shouldn't exist in this specific pattern. James Webb revealed them anyway. Samuel Crowe offered one more observation. The image from Webb is stunning, and the science we will get from it is even better. The needles are a mystery, the protostars are a puzzle, the whole region challenges expectations. And it sits just 300 light-years from our galaxy's screaming heart. The galactic center is not empty space. James Webb's near-infrared camera captured a region 50 light-years wide. The image glows with approximately 500,000 stars, each one a nuclear furnace, each one burning hydrogen into helium, each one fighting against gravity's crush. 500,000 stellar engines packed into a volume that seems impossibly small. For comparison, the nearest star to Earth sits over 4 light-years away. Our stellar neighborhood is sparse, empty, lonely. The galactic center operates under different rules. Stars crowd together like people in a subway car. The average distance between them shrinks to astronomical insignificance. This density changes everything. In quiet regions of the galaxy, stars form slowly. A cloud of gas collapses, takes millions of years to gather enough mass, finally ignites. The process is methodical, patient, stable. Near Sagittarius A star, stellar birth happens in cosmic minutes. Gas compresses rapidly under extreme gravity. Stars pop into existence like firecrackers. The environment should make star formation impossible. Intense radiation from existing stars heats the gas. Hot gas expands. Expanded gas resists compression. No compression means no stars. This is basic physics. The galactic center ignores it completely. The region also experiences tidal forces. Sagittarius A star's gravity stretches and squeezes everything nearby. Gas clouds get torn apart. Stellar orbits become chaotic. Objects that wander too close get shredded. Yet somehow, stars keep forming in this gravitational meat grinder. Samuel Crowe raised an important question. Are more massive stars formed in the center of our galaxy compared to the edges of its spiral arms? The answer matters for understanding cosmic evolution. Massive stars live fast, die young, explode as supernovae. These explosions seed the universe with heavy elements: carbon, oxygen, iron, all the atoms that make planets and people. If the galactic center preferentially creates massive stars, it functions as a cosmic forge, pumping out heavy elements faster than anywhere else. These elements eventually spread throughout the galaxy, mix into new stellar generations, build rocky worlds, enable complex chemistry, maybe even life. The 500,000 stars visible in Webb's image represent only what the telescope can detect. Countless more hide behind dust, lurk in the infrared dark clouds, orbit in the gaps between visible clusters. The true stellar population probably exceeds 1 million, all packed into 50 light-years. That density creates interactions impossible elsewhere. Stars pass close to each other. Gravitational nudges alter orbits. Some stars get ejected from the region entirely. Others fall deeper into the gravity well. A few spiral inward towards Sagittarius A star itself. When stars approach the black hole, tidal forces rip them apart. The process is called spaghettification. Gravity pulls harder on the near side than the far side. The star stretches, elongates, eventually tears into a stream of gas. This gas feeds the black hole, adds to the accretion disk, fuels the constant flares. The galactic center also hosts stellar remnants, white dwarfs, neutron stars, smaller black holes. These corpses of dead stars populate the region like ghosts. Some orbit peacefully, others collide. When neutron stars merge, they release gravitational waves. These ripples in space-time propagate outward at light speed. Observatories on Earth detect them as faint vibrations. 500,000 stars shine in the darkness, each one a story of survival in the galaxy's most hostile neighborhood, each one defying the chaos around it, each one screaming silently into the void. James Webb captured them all in a single image. At the heart of darkness, something massive is being born. Deep within an infrared dark cloud near Sagittarius C, a protostar grows, still forming, still pulling in gas from its surroundings, already 30 times as massive as our star. This infant will dwarf most stars in the galaxy when it finishes developing. The cloud surrounding it blocks all visible light. Background stars disappear completely. The region appears as a black hole in the image, though it's not a true hole, just darkness so complete that even James Webb's sensitive instruments struggle to penetrate. The protostar hides within like a monster in its cave, but it's not hiding completely. Outflows glow at the cloud's edges. The forming star shoots jets of material perpendicular to its rotation. These jets plow through surrounding gas, create glowing shock waves, reveal the protostar's presence even though we cannot see it directly, like finding a predator by the wake it leaves. 30 solar masses, while still forming, represent something rare. Most stars tap out around 1 or 2 solar masses. Giants might reach 10 or 15. True monsters that exceed 20 solar masses form only in special conditions. The galactic center provides those conditions: extreme density, powerful gravity, abundant gas, everything needed to build a stellar titan. These massive protostars live fast lives. Once fusion ignites in their cores, they burn through fuel at terrifying rates. A typical star might shine for 10 billion years. These monsters last a few million. Cosmic mayflies. They blaze bright and die young. Their deaths are spectacular. When fusion stops, gravity wins. The core collapses in seconds. The outer layers rebound. A supernova explosion tears through space. For a brief moment, one dying star outshines an entire galaxy. The explosion scatters heavy elements across light years, seeds the cosmos with the raw materials for new worlds. If the core is massive enough, no explosion occurs. Gravity crushes everything into a black hole. The stellar corpse disappears from the visible universe, leaves only a gravitational footprint. These stellar mass black holes eventually migrate toward galactic centers, merge with other black holes, feed supermassive monsters like Sagittarius A star. The protostar at Sagittarius C will probably explode. 30 solar masses sits near the boundary, heavy enough to go supernova, possibly light enough to avoid direct collapse. The question matters for understanding how galaxies evolve. Supernovae pump energy into their surroundings, trigger new star formation, shape galactic structure. Without these explosions, galaxies would look completely different. The dense cloud hosting this protostar contains more stellar infants. Dozens of smaller protostars scatter through the darkness, each one pulling in gas, each one growing, each one racing toward the moment when fusion ignites. The cloud glows like a bonfire in infrared, invisible to human eyes, blazing in the wavelengths James Webb sees. Around this cluster, smaller infrared dark clouds dot the landscape. These are the next generation, future stellar nurseries, places where stars haven't started forming yet. Give them a few million years, they'll light up just like the current cluster. The galactic center breeds stars constantly. The process never stops. Gas flows inward under gravity's pull, compresses, heats, ignites. New stars join the crowd. The cycle continues endlessly. That protostar hiding in darkness will join the 500,000 stars already shining. It will burn brighter than almost all of them, pump out more energy than 100 typical stars combined. Its radiation will sculpt the surrounding gas, create new structures, possibly trigger new star formation. For now, it grows in secret, adding mass, building toward ignition, preparing for a brief, violent, spectacular life. And James Webb watches from 26,000 light-years away, capturing its birth in infrared detail. Turn James Webb toward the early universe. Count the galaxies. Notice something impossible. Over 1,600 disk galaxies stare back at us. Each one resembles our own galaxy, spiral arms, central bulges, rotating disks of stars. The architecture is familiar, comforting, normal. The timing is not. These galaxies existed 9 to 13 billion years ago, when the universe was young, when violent mergers should have dominated, when fragile spiral structures had no business surviving. Yet there they are, warped like vinyl records, delicate, organized, impossible. The discovery came from analyzing nearly 4,000 galaxies in Webb's deep field images. Astronomers measured their distances, determined their ages, classified their shapes. The results defied predictions. 42% were disk galaxies, nearly half. Previous theories said this shouldn't happen. Early universe equals chaos. Dwarf galaxies smashing together, mergers destroying delicate structures, elliptical blobs forming instead of elegant spirals. The math was clear. The predictions were confident. James Webb looked and found something else entirely. Disk galaxies, like our own, require specific conditions. Gas must flow inward steadily, must settle into a rotating disk, must avoid major collisions that would disrupt the structure. The process takes billions of years in computer simulations. Patience, stability, time. The early universe offered none of these luxuries. Space was cramped, galaxies crowded together, collisions happened constantly. The environment was hostile to fragile structures. Spiral arms should have been smeared out of existence, twisted apart, destroyed. They survived anyway. More than that, they thrived. The disk galaxies in the early universe look healthy, active, forming stars, building stellar populations, operating as if violent mergers weren't constantly threatening their existence. Gabriel Perez Diaz illustrated several of these ancient disk galaxies. The images show galaxies that could be mistaken for our own cosmic backyard. Replace the redshift labels with local distances, and nobody would question them. Perfect spirals, orderly structure, no signs of recent violence. This changes our understanding of galaxy evolution. If disk galaxies formed and survived this early, the standard merger-driven model needs revision. Maybe galaxies assembled faster than we thought. Maybe they were more resilient than simulations predicted. Maybe early conditions weren't as hostile as we assumed. The implications extend to life itself. Disk galaxies often host life-friendly conditions, stable environments, rich in heavy elements, plenty of gas for planet formation. If disk galaxies dominated the early universe, life could have started earlier than we thought, billions of years before Earth formed. Civilizations might have risen and fallen, while our star was still a cloud of gas. The Milky Way sits in today's universe, 13.8 billion years old. Mature, stable. We assumed we were typical, that our galaxy's history matched the standard timeline. Slow assembly, gradual growth, billions of years of mergers culminating in our current state. James Webb found our twins living in the cosmic past, already assembled, already spinning, already looking like home when the universe was barely 1/10 its current age. Astronomers expected to find galaxy formation in progress, messy construction zones, half-built structures, evidence of the violent process. Instead, they found finished products, complete galaxies, as if someone fast-forwarded through the construction phase and jumped straight to the result. The universe was more organized in its youth than anyone predicted, more structured, more mature. The infant cosmos had developed faster than its age should allow. Over 1,600 impossible galaxies fill the ancient sky, each one a mirror reflecting our own, each one questioning everything we thought we understood about cosmic history. 1.5 billion years after the Big Bang, something perfect appears. The galaxy is called Alaknanda, named after a Himalayan river. It resembles the Milky Way in almost every detail. Spiral arms sweep around a bright central bulge. The disk rotates smoothly. Stars form in orderly patterns, a mature, elegant structure. The universe at this time was 1/10 its current age. Galaxies should still be assembling, building themselves piece by piece. Messy, chaotic, incomplete. Alaknanda looks finished. Rashi Jain discovered this galaxy, a researcher at the National Center for Radio Astrophysics in India. The discovery came from analyzing James Webb images. When the data arrived, it challenged everything Jain knew about galaxy formation. The galaxy stretches about 30,000 light-years across, smaller than the Milky Way, but not by much. It contains 10 billion solar masses of stars. That's a tremendous stellar population for such a young age. These stars didn't form gradually over billions of years. They assembled in just a few 100 million years. Do the math, 10 billion stellar masses in a few 100 million years. That requires forming stars at an incredible pace. Alaknanda creates the equivalent of 60 stellar masses every year. Compare that to our galaxy. The Milky Way forms 1 or 2 new stars annually. Alaknanda works 20 times faster. Half of the galaxy's stars formed in just 200 million years. Imagine compressing billions of years of stellar evolution into 2% of that time. The galaxy assembled like a building constructed in time-lapse. Impossibly fast, impossibly efficient. The structure shows 2 distinct, symmetric spiral arms. Classic grand design spiral. These patterns require density waves propagating through the galactic disk. Gas gets compressed as it passes through these waves. Compression triggers star formation. The stars light up the spiral arms. The whole system operates like cosmic clockwork. Creating density waves takes time. The disk must settle, must reach stability, must develop the gravitational choreography that sustains spiral patterns. Simulations suggest this process requires several billion years. Alaknanda managed it in a fraction of that time. Yogesh Wadadekar, co-author of the study, summarized the problem. Alaknanda reveals that the early universe was capable of far more rapid galaxy assembly than we anticipated. The galaxy exists. The data is clear. The theories are wrong. Two possible explanations exist. First, cold gas might have flooded into the galaxy at extreme rates, faster than any model predicted. This rapid inflow would fuel intense star formation, build the stellar population quickly, create the observed structure. Second, a small galaxy might have collided with Alaknanda early in its life. The collision could have triggered the spiral arms, jump-started star formation, accelerated development. However, collision-induced spirals usually fade quickly. Alaknanda's spirals look permanent, stable, well-established. Future observations might distinguish between these scenarios. If the galaxy's rotation is smooth, it probably formed through rapid gas accretion. If the rotation shows turbulence, a collision might be responsible. James Webb will observe Alaknanda again, study its motion, measure its properties more precisely. For now, the galaxy stands as evidence. Proof that the early universe assembled structures at speeds we didn't think possible. Alaknanda formed in cosmic minutes, built a mature spiral in a fraction of the expected time, appeared fully developed when it should barely be starting. The galaxy sits in deep space, magnified by gravitational lensing from Pandora's cluster, a massive galaxy cluster between us and Alaknanda. The cluster's gravity bends light, acts like a cosmic magnifying glass, allows James Webb to see details that would otherwise be impossible. Alaknanda is named for good reason. The Himalayan river joins the Mandakini to form the Ganga. Mandakini is the Hindi word for Milky Way. Two rivers joining, two galaxies mirroring each other across cosmic time. One ancient, one modern, both impossible. 1 billion years after the Big Bang, a dragon opens its eyes. The galaxy is called Zhulong, torch dragon, in Chinese mythology, a creature whose eyes controlled day and night. Opening them brought light, closing them brought darkness. The name fits. This galaxy blazes across the infant cosmos like a solar entity waking from sleep. Mengyuan Xiao discovered Zhulong while analyzing survey data. The University of Geneva researcher spotted it in images from James Webb's panoramic survey. The telescope was observing one region when it accidentally captured another. Pure parallel mode. Two instruments watching two different areas simultaneously. What emerged from the data was remarkable. Zhulong resembles the Milky Way in shape, size, stellar mass, a central bulge of old stars, a vibrant disk forming new ones, two distinct spiral arms. The architecture is familiar. The timing is not. The galaxy existed when the universe was 1/14 its current age. Less than 8% of cosmic history had passed. Galaxies should look like chaotic blobs, messy collections of stars without clear structure. Zhulong displays perfect organization. The disk spans 60,000 light-years, slightly smaller than the Milky Way's 100,000 light-year breadth, still massive by any measure. The stellar mass reaches 100 billion times that of our star, more than double the Milky Way's current stellar population. Think about that. Zhulong contains more stars than our galaxy, yet it formed in 1/14 the time. The early universe assembled structures faster than the modern cosmos, like watching evolution in fast forward. Christina Williams leads the panoramic survey. Her explanation for finding such rare objects highlights Webb's unique capabilities. This allows JWST to map large areas of the sky, which is essential for discovering massive galaxies, as they are incredibly rare. Pure parallel mode doubles observation efficiency, captures twice the data in the same time. Zhulong's location helped with detection. Gravitational lensing from foreground galaxies magnified its light, made it brighter and larger in the images, allowed detailed study that would otherwise be impossible. The universe provided a natural telescope to supplement our artificial one. The galaxy's features defy standard formation theories. Those theories predict slow assembly. Galaxies start small, gradually merge, build mass over billions of years, eventually develop spiral arms after reaching maturity. The process should take most of cosmic history. Xulong skipped the assembly phase, appeared fully formed, already spinning, already sporting organized structure, as if someone built it off-screen and placed it in the early universe completely finished. The spiral arms pose particular problems. These structures are delicate, easily disrupted. Major mergers destroy them instantly. The early universe was crowded. Collisions were common. Spiral arms shouldn't survive in that environment. Yet, Xulong's spirals look pristine, undisturbed, well-defined. Either the galaxy avoided collisions through incredible luck, or spiral structures are more resilient than simulations suggest. The central bulge contains older stars. These stars formed even earlier than the disk population, meaning star formation started when the universe was even younger, maybe 800 million years after the Big Bang, maybe 700 million. The timeline keeps compressing. Xulong's discovery adds to growing evidence. James Webb keeps finding mature galaxies in the early universe. Each discovery challenges standard cosmology. Each observation demands explanation. The telescope reveals a cosmos that developed faster than theories allow. The Dragon Galaxy stares back across 12.8 billion light-years. Its light has traveled most of cosmic history to reach us. When that light left Xulong, the universe was barely breathing. When it arrives at James Webb, the universe is ancient. Mengyuan Zhao summarized the significance. What makes Xulong stand out is just how much it resembles the Milky Way in shape, size, and stellar mass. We're looking at our own reflection in the cosmic past, seeing ourselves as we might have been if we had existed impossibly early. The dragon's eyes remain open, shining across the void, showing us what the early universe really looked like. And it's nothing like we expected. Scan deep field images from James Webb. Count the unusually bright objects. Stop at 300. These objects glow far brighter than they should. Located in the early universe, shining with intensities that current models cannot explain. Each one challenges our understanding of how galaxies form and evolve. Haojing Yan discovered them, an astronomy professor at the University of Missouri. His team analyzed infrared images captured by Webb's near-infrared camera. The objects appeared as bright spots scattered throughout the ancient cosmos. Too many of them, too bright, too early. The problem is simple physics. Brightness comes from stars. More stars means more light, but forming stars takes time. Gas must collapse, cores must ignite, stellar populations must build. The early universe hadn't existed long enough to create the massive stellar populations these brightness levels require, unless something else is happening. Bangzheng's son works with Yan on this research. His assessment was direct. These mysterious objects are candidate galaxies in the early universe, meaning they could be very early galaxies. The word candidate matters. Scientists cannot be certain what these objects are without additional observations. Spectroscopy will provide the final answer. Breaking light into different wavelengths reveals an object's chemical composition, distance, physical properties, age, everything needed to confirm identity. The team has already spectroscopically confirmed one object as an early galaxy. That confirmation proves these objects exist. The question is what fraction of the 300 are real? If even a few turn out to be genuine early galaxies, cosmology has a problem. The standard model of galaxy formation cannot produce objects this bright this early. Either galaxies formed faster than we thought, or they were more efficient at forming stars, or our understanding of stellar populations is fundamentally wrong. The third option is intriguing. Maybe early stars behave differently than modern ones. Different mass distributions, different luminosities, different lifetimes. The early universe had different conditions. Less heavy elements, denser gas, stronger radiation fields. These conditions might produce stellar populations unlike anything we see today. Some of these bright objects might not be galaxies at all. Alternative explanations exist. Active supermassive black holes can shine extremely bright. Quasars outshine entire galaxies. If some of these 300 objects are quasars rather than galaxies, the brightness puzzle solves itself. But that creates a different puzzle. Where did supermassive black holes come from so early? These monsters require time to grow. They start small, feed gradually, build mass over cosmic history. Finding them fully formed in the infant universe demands explanation. The objects fill a wide region of sky, scattered throughout deep field images, not clustered in one area. This distribution suggests they represent a common phenomenon rather than rare flukes. The early universe might have been much more active than we realized. Brightness varies among the 300 objects. Some shine moderately bright, others blaze intensely. This range suggests different stages of development or different object types. Perhaps early galaxies came in more varieties than modern ones. Perhaps the early universe produced cosmic entities we don't see today. Hao Jingyan outlined the stakes. If even a few of these objects turn out to be what we think they are, our discovery could challenge current ideas about how galaxies formed in the early universe, the period when first stars and galaxies took shape. Cosmic dawn, the era we thought we understood. James Webb keeps revealing we understood very little. The telescope's sensitivity makes these discoveries possible. Previous instruments lacked the power to detect these distant, faint objects. Even though they shine brightly for their era, 13 billion light-years of distance dims them considerably. Webb's mirror captures enough light to reveal them anyway. 300 impossible lights burn across the ancient sky, each one a mystery, each one demanding explanation, each one suggesting the early universe operated under different rules than we assumed. Spectroscopy campaigns are underway. More observations planned. The team will confirm identities, measure properties, determine what these objects really are. The answers will reshape our understanding of cosmic history. For now, they remain candidate galaxies, bright mysteries, impossible lights that probably shouldn't exist. Yet there they shine. Something glows in the extreme early universe. Scientists cannot tell you what it is. The object is called Capitoro, bullhead in Italian, discovered in images showing the cosmos just 100 million years after the Big Bang. If this is a galaxy, it's the earliest ever found. If it's something else, cosmology just got more complicated. The timing alone is terrifying. 100 million years. That's less than 1% of the universe's current age. The cosmic dark ages had barely ended. The first stars were just igniting. Nothing complex should exist yet. Capitoro exists anyway. The object shines far too bright. Galaxies at this distance should be faint, limited by how quickly they can form stars, constrained by available gas, throttled by cosmic conditions. Capitoro blazes like it, doesn't care about constraints. Giovanni Gandolfi studies this object, an astrophysicist at the National Institute of Astrophysics in Italy. His description captures the confusion perfectly. Capitaro, whatever it is, seems really interesting and promising. Scientists don't even know what category to place it in. 3 possibilities exist. First, it could be an extremely early galaxy, born when the universe was barely breathing, forming stars at impossible rates, creating light through stellar fusion. This explanation requires rewriting galaxy formation theories. Stars don't assemble this fast, shouldn't shine this bright this early. Second, it might be a supermassive black hole actively feeding on surrounding gas, outshining its host galaxy, blazing as a quasar. This explanation also breaks theories. Where did the black hole come from? How did it grow so massive so quickly? Supermassive black holes need time to develop. 100 million years isn't enough. Third, it could be something entirely new, a class of cosmic object we've never seen, some phenomenon unique to the extreme early universe, operating under conditions that no longer exist. This is the most unsettling possibility. Unknown categories scare scientists more than wrong theories. Muhammad Latif evaluated Kapotaro from outside the research team, an astrophysicist at United Arab Emirates University. His assessment was blunt. "It's one of the most puzzling discoveries," he continued. "It's a very intriguing object in the sense that whatever the way you interpret it, it basically is kind of pushing the boundaries of our knowledge to the edge." All three explanations require major revisions to cosmology. If it's a galaxy, galaxy formation happens much faster than we thought. If it's a black hole, black holes grow much faster than we thought. If it's something new, we don't understand the early universe at all. The name Kapotaro comes from its appearance. The object shows unusual features that reminded researchers of a bull's head: bright central region, fainter extensions, odd morphology, unlike standard galaxies or quasars. Even visually, it refuses to fit categories. Distance measurements put it at redshift 13 or higher, meaning we see it as it existed 13 billion years ago or more. The light has traveled most of cosmic history to reach us. When that light left Kapotaro, the universe was in its infancy. Spectroscopic observations will provide answers. Breaking the light into wavelengths reveals chemical composition, motion, temperature, energy sources, all the clues needed to identify the object. The research team has requested additional James Webb time, wants to study Kapotaro in more detail, pin down its nature. They're also searching for similar objects. If Kapotaro is unique, it might be a fluke, an outlier, an exception that proves the rule. But if similar objects exist throughout the early universe, the implications multiply. A whole population of unknown entities lurking in cosmic dawn. Kapotaro sits in the data like a riddle, clear enough to detect, mysterious enough to confound explanation, bright enough to demand attention, strange enough to resist identification. Whatever it is, it shouldn't exist. Not this early, not this bright, not this bizarre. James Webb found it anyway. Now cosmology must explain it. A new species invades the early universe. They're called little red dots, small red objects scattered throughout images of cosmic dawn, discovered by James Webb in large numbers around 600 million years after the Big Bang. Mysterious, abundant, unexplained. The name describes them perfectly. They appear as tiny red points in deep field images, compact, bright for their size, distinctly colored, each one identical to the others, like cosmic copies stamped from the same template. What makes them red? Distance stretches light. The farther away an object sits, the more its light shifts toward the red end of the spectrum. Little red dots are extremely distant. Their light has traveled over 13 billion years. This journey stretches visible light into infrared, makes them appear red even though they might emit other colors. But that's just optics. The real mystery is what they are. Initial observations suggested small, very distant galaxies, forming stars, building stellar populations, standard cosmic citizens. Then astronomers looked closer. The properties didn't match standard galaxies. Too compact, too bright for their size, too uniform in appearance. Spectroscopic analysis revealed something stranger. Some little red dots show signs of active supermassive black holes, accreting matter, spewing energy, shining as quasars. But they're too small to be typical quasars, too numerous, too evenly distributed. One little red dot called Virgil displays Jekyll and Hyde behavior. Sometimes it looks like a normal young galaxy, quietly forming stars, minding its business. Other times it transforms into a feeding monster, a heavily obscured supermassive black hole pouring out immense energy. Dust obscures these black holes. Thick clouds absorb visible light. Only infrared escapes. James Webb's infrared vision penetrates the dust, reveals what's happening inside. Without Webb, these objects would remain invisible, hidden behind cosmic fog. The little red dots appear around 600 million years after the Big Bang. Peak in population, then disappear by the time the universe reaches 2 billion years old. This timeline raises questions. Where did they come from? Where did they go? What happened to them? The transformation theory suggests they evolved into something else. Changed form, became objects we see in the modern universe. Identifying their descendants would solve the mystery, but astronomers haven't figured out what modern objects descended from little red dots. Virgil might provide the answer. If astronomers can watch it transform, they'll understand the process. See what little red dots become. Connect the ancient mystery to modern populations. The sheer number of little red dots is concerning. They're not rare exceptions. They swarm throughout the early universe. Every deep field image contains dozens. This abundance suggests they represent a common phase of cosmic evolution, something most early galaxies or black holes experienced. Some researchers think little red dots are extremely dusty quasars, supermassive black holes wrapped in thick dust cocoons. The dust absorbs radiation from the black hole, re-emits it as infrared, creates the compact red appearance. This would explain their brightness and color. Others think they might be compact starbursts, galaxies forming stars at extreme rates in tiny volumes. The density creates intense radiation, heats surrounding dust, produces infrared glow, but this doesn't explain the black hole signatures some little red dots display. A third possibility involves black hole stars, hypothetical objects where a black hole sits inside a star. The star feeds the black hole continuously. The black hole radiates energy outward, creates a hybrid object unlike anything we see today. This exotic possibility remains unconfirmed. The truth might involve all three categories. Some little red dots could be dusty quasars, others compact starbursts. A few might be something entirely unknown. The population might be diverse despite their visual similarity. Researchers need more data, more spectroscopy, more observations at different wavelengths. James Webb will continue studying these objects. Other telescopes will contribute. Eventually, the mystery will yield. For now, hundreds of little red dots haunt the early universe. Ancient red entities, too numerous to ignore, too strange to explain. Each one a cosmic question mark floating in the primordial darkness. They dominated the young cosmos for over 1 billion years, then vanished. Their descendants hide somewhere in the modern universe, wearing disguises we haven't penetrated. James Webb keeps watching, keeps collecting data, keeps hoping to catch one transforming. Meet Virgil, the galaxy with two personalities. Observed in different wavelengths, Virgil shows completely different characteristics. At some frequencies, it appears as a typical young galaxy, quietly forming stars, building stellar populations. Operating normally, switch wavelengths, and everything changes. The mild-mannered galaxy transforms into a cosmic monster, a heavily obscured supermassive black hole pouring out immense energy. The dual nature makes Virgil one of the strangest little red dots. Most objects display consistent properties across wavelengths. Stars shine as stars. Black holes shine as black holes. Virgil refuses to pick a side. The research team described it perfectly. Virgil has two personalities, its good side, a typical young galaxy quietly forming stars. But Virgil transforms into the host of a heavily obscured, supermassive black hole, pouring out immense quantities of energy. How does one galaxy maintain two identities? Dust provides the answer. Thick clouds surround the central black hole. These clouds absorb some wavelengths of light, allow others to pass through. Different instruments see through different types of dust, create different views of the same object. At visible wavelengths, the dust blocks the black hole completely. Only the surrounding galaxy shows through. Stars forming in the outer regions, gas clouds collapsing. Normal galactic activity. This is Virgil's good side, the face it shows to visible light telescopes. At mid-infrared wavelengths, the black hole emerges. Dust becomes transparent. The accretion disk blazes into view, intense radiation, particle jets, all the signatures of an active supermassive black hole feeding aggressively. This is Virgil's monster side, the truth hidden behind the dust. James Webb's MIRI instrument captured the transformation. MIRI operates in mid-infrared, sees through cosmic dust better than almost any other instrument. When pointed at Virgil, MIRI revealed the black hole hiding inside, showed the galaxy's true nature. The implications extend beyond Virgil. If one galaxy can hide its black hole behind dust this effectively, others probably do the same. Astronomers might be blind to a whole population of dust-obscured supermassive black holes. These monsters could be everywhere, feeding silently, growing in secret, contributing to cosmic evolution without revealing themselves. The research paper raised this possibility directly. Are we simply blind to its siblings because equally deep MIRI data have not yet been obtained over larger regions of the sky? The answer is probably yes. Virgil represents the tip of an iceberg. Most of the iceberg remains hidden. These obscured black holes might explain how supermassive black holes grew so large so quickly. If they spent their early years wrapped in dust, feeding continuously without interference, they could accumulate mass faster than expected. The dust shields them from radiation pressure that would normally limit feeding rates. Virgil existed 600 million years after the Big Bang, when the universe was young, when everything should be visible and simple. Instead, complexity already dominated. Galaxies wore disguises. Black holes hid behind veils. The cosmic costume party was in full swing. The transformation between Virgil's two faces isn't instantaneous. The galaxy doesn't flicker back and forth. Instead, the different wavelengths reveal different components existing simultaneously. The star-forming galaxy and the feeding black hole operate at the same time, one visible, one hidden, both real. This teaches an important lesson about cosmic observations. What we see depends on how we look. Different wavelengths reveal different truths. Relying on one type of light creates blind spots. Only by observing across the spectrum can we see the complete picture. Virgil forces astronomers to question other observations. How many galaxies in the early universe hide similar secrets? How many quiet star formers actually host active black holes beneath dust cocoons? How many cosmic monsters masquerade as mild-mannered galaxies? The answers will require more MIRI observations, more mid-infrared surveys, more dust-penetrating investigations. James Webb can provide this data. The telescope was designed for exactly this purpose, finding things hidden in plain sight. Virgil's dual nature makes it extraordinary, but it probably isn't unique. The galaxy likely represents a common phenomenon we're just beginning to recognize, a whole population of Jekyll and Hyde galaxies lurking in the early universe. Each one wearing two faces, each one hiding its true nature behind dust, each one waiting for James Webb to reveal its secret. A galaxy sits in the ancient cosmos. It shouldn't exist. The galaxy is designated ZFUD S7329. Discovered in James Webb images showing the universe 800 million years after the Big Bang. More massive than the Milky Way despite forming incredibly early, contains more stars than our entire galaxy, exists when it theoretically cannot. The problem is dark matter, or rather, the lack of it. Current cosmology depends on dark matter. This invisible substance outweighs normal matter 5-1. Provides gravitational scaffolding for galaxy formation. Without dark matter, galaxies cannot assemble. The math is clear. Observations confirm it. Dark matter is fundamental to cosmic structure. ZFUDS 7329 formed too early for sufficient dark matter structures to exist. The timeline doesn't work. Dark matter clumps grow slowly. Take hundreds of millions of years to reach galaxy hosting size. At 800 million years post-Big Bang, they weren't ready yet. Somehow, this galaxy assembled anyway. Claudia Lagos studies this object, an associate professor at the International Center for Radio Astronomy Research. Her assessment was direct. Having these extremely massive galaxies so early in the universe is posing significant challenges to our standard model of cosmology. The galaxy contains more stars than the Milky Way. Our galaxy spent over 13 billion years building its stellar population. Accumulated stars through countless mergers gradually grew to its current mass. ZFUDS 7329 reached similar mass in less than a billion years. The formation speed defies explanation. Stars form from gas. Gas must cool and collapse. Cooling takes time. Collapse takes time. Fusion ignites. Stars shine. More gas collapses. More stars form. The cycle proceeds gradually. Even under ideal conditions, star formation has speed limits. ZFUDS 7329 ignored these limits. Formed stars at rates standard physics shouldn't allow. Built a massive, stellar population before the universe had time to prepare the necessary conditions. Dark matter structures grow through gravitational collapse. Small fluctuations in density slowly amplify. Dense regions pull in more matter, become denser, pull harder. The feedback loop creates dark matter halos. These halos provide gravitational wells for normal matter to fall into. Galaxies form within these wells. This process requires time. The early universe was smooth, nearly uniform. Small density variations existed, but amplification was just beginning. By 800 million years, dark matter halos had formed, but they were small, insufficient for hosting massive galaxies. Yet ZFUDS 7329 exists. Massive, mature, fully formed. Three possibilities emerge. First, galaxy formation is much more efficient than we realized. Maybe gas converts to stars faster in the early universe. Different conditions, different physics, higher efficiency. This wouldn't solve the dark matter timing problem, but would explain the rapid star formation. Second, dark matter structures might grow faster than simulations predict. Maybe our models underestimate early gravitational collapse. Maybe dark matter clumps more aggressively than we thought. This would provide the necessary halos for early galaxy formation. Third, our understanding of dark matter is wrong. Maybe it behaves differently than we assume. Maybe it doesn't provide the gravitational scaffolding we think it does. Maybe galaxies can form without it. This possibility terrifies cosmologists. Dark matter underpins modern cosmology. Removing it collapses the entire framework. The research team favors the first two possibilities. They suggest modifications to existing theories rather than wholesale replacement. Adjustments to star formation efficiency, tweaks to dark matter dynamics, conservative changes that preserve the overall picture, but ZFUDS 7329 might demand radical revision. The galaxy exists 11.5 billion light-years away. We see it as it was in the distant past. The observation is clear. The data is solid. The galaxy is real. Theories must adapt to reality, not the other way around. More observations are planned, studying similar early massive galaxies, determining if ZFUDS 7329 is unique or representative. If many such galaxies exist, the problem intensifies. If this galaxy is alone, it might be an outlier, an exception, a fluke of cosmic variance. Either way, it challenges the standard model, forces uncomfortable questions, demands answers cosmology cannot currently provide. ZFUDS 7329 stands as evidence. A massive galaxy, born too early, assembled too quickly, existing despite theoretical impossibility. Dark matter's grip on galaxy formation loosens. The scaffolding cracks, and James Webb keeps finding more impossible galaxies in the ancient sky. Red stars fill the ancient universe. This should not happen. James Webb's deep field images reveal galaxies glowing with mature red light, stars that have aged, burned through their fuel, cooled from bright blue to deep red. These elderly stars populate galaxies barely born. The contradiction is stunning. Stars age predictably. Young stars burn hot, emit blue-white light. As they exhaust hydrogen fuel, they cool. Their output shifts toward red. The process takes billions of years for typical stars. Seeing red stars in ancient galaxies means those stars are already old when the universe itself is young. Joel Lager analyzed these observations, assistant professor at Penn State. His description captured the confusion. We had specific expectations for the type of galaxies that live in the early universe. They are young and small. Young galaxies should contain young stars, blue stars, hot stars, recently ignited stellar infants. The observations showed something else. Galaxies only 500 to 700 million years post-Big Bang already contained red stellar populations, mature stars that had lived and aged, in a universe barely old enough for stars to exist at all. The galaxies appeared as tiny reddish dots, faint, distant, ancient. By analyzing the light they emitted, astronomers determined their ages, measured their stellar populations, confirmed they contained mature stars. With age, stars develop redder appearance as they burn through fuel and cool down. The color shift indicates advanced stellar evolution. These galaxies showed that shift, meaning their stars had already aged significantly despite the universe's youth. The galaxies were also massive, 50 times more massive than early predictions suggested. Some approached the Milky Way's current mass, galaxies as heavy as our own existing when the universe was 3% its current age. This combination is lethal to standard theories. Massive galaxies require billions of years to assemble. Red stars require billions of years to age. The early universe provided neither, yet both appeared together in the same galaxies. The Hubble Space Telescope missed these objects. Hubble looked for small blue galaxies in the early universe. Expected baby galaxies, tiny stellar collections just beginning. Found those galaxies, missed the massive red ones entirely. James Webb's infrared vision revealed what Hubble couldn't see. The red light from ancient galaxies shifts into infrared during its long journey. Webb detects infrared. Hubble primarily detects visible light. This capability gap meant Hubble observed one population while missing another. The reddish dots raise uncomfortable questions. If galaxies this massive existed this early, galaxy formation models are fundamentally broken. If stars this old existed this early, stellar evolution timelines are wrong. If both are true, multiple pillars of astrophysics collapse simultaneously. Before rewriting theories, astronomers want confirmation. Spectroscopy will provide it. Breaking light into component wavelengths reveals exact distances, chemical compositions, ages. Everything needed to verify these galaxies are what they appear to be. Some reddish dots might be something else. Dusty objects, red in color but not in stellar population. Objects at different distances than estimated. Spectroscopy will distinguish true red stellar populations from imposters. But initial spectroscopy already confirmed at least one massive ancient galaxy. The verification proved these objects exist, demonstrated the observations are real. Now the question becomes how common they are. If numerous massive red galaxies populate the early universe, cosmology faces a crisis. The standard model cannot produce them. Modifications might help. Adjustments to star formation rates, changes to merger timelines, tweaks to various parameters. Or maybe the modifications won't be enough. Maybe the entire framework needs replacement. Maybe galaxy formation operates under principles we haven't discovered. Maybe the early universe followed different rules than the modern cosmos. The reddish dots glow in James Webb's images. Ancient galaxies, mature stars, impossible timelines, each one a puzzle, each one a challenge, each one demanding explanation. Crimson light from cosmic dawn, evidence that the universe grew up faster than we ever imagined. The early universe bred titans, stars so massive they make our stellar neighborhood look like insects. Astronomers call them monster stars, theoretical objects with masses reaching 10,000 times that of our star, burning brilliantly for brief cosmic moments before collapsing into black holes, leaving behind chemical signatures detectable billions of years later. Evidence for these stellar dinosaurs comes from a galaxy called GS 3073. Light from this galaxy traveled over 13 billion years to reach James Webb. When that light departed, the universe was in its infancy. The galaxy shows unusual chemical fingerprints. Nitrogen and oxygen exist in wrong proportions. Daniel Whalen studies these objects at the University of Portsmouth. His description emphasizes their brief existence. These cosmic giants would have burned brilliantly for a brief time before collapsing into massive black holes, leaving behind the chemical signatures we can detect billions of years later. He compared them to dinosaurs, enormous, primitive, short-lived. Monster stars would live only 250,000 years, a cosmic blink. For comparison, our star will shine for 10 billion years. Monster stars burn 40,000 times faster, exhaust their fuel almost immediately, die while the universe is still young. These titans would form only under special early universe conditions, less heavy elements, purer hydrogen and helium gas, different chemistry, different physics. The pristine gas of cosmic dawn could collapse into objects far more massive than modern star-forming regions allow. 10,000 solar masses concentrated in one star creates unimaginable conditions. Core temperatures reaching hundreds of millions of degrees, radiation pressure fighting against gravitational collapse, nuclear fusion proceeding at terrifying speeds, the whole object teetering on the edge of instability. When fusion stops, gravity wins. The core collapses in seconds, but the star is too massive for a normal supernova. Instead, it collapses directly into a black hole. No explosion, no fireworks. Just a sudden transition from brilliant star to invisible singularity. These stellar mass black holes would be enormous, hundreds or thousands of times heavier than typical stellar remnants. They would quickly sink toward galactic centers, merge with each other, feed the growth of supermassive black holes. This process might explain how supermassive black holes grew so large so quickly. Monster stars provided seed black holes, already massive when born, growing rapidly through mergers, accumulating enough mass to explain the supermassive monsters we observe in ancient galaxies. The chemical signature in GS 3073 provides the smoking gun. Normal stars produce certain ratios of elements. The ratios in this galaxy don't match. Too much nitrogen relative to oxygen. No known stellar population produces this imbalance, except monster stars. Their extreme conditions would create unusual nuclear reactions, produce elements in different proportions, leave fingerprints unlike anything modern stars create. The chemical anomaly in GS 3073 matches predictions for monster star pollution. This represents first observational evidence these titans existed. Until now, monster stars were purely theoretical, proposed to solve black hole growth problems, predicted by simulations, never detected. GS 3073 changes that. The galaxy sits 13 billion light-years away. We observe it as it existed in the early universe. The monster stars themselves are long dead, collapsed into black holes billions of years ago. But their chemical legacy remains, imprinted on the gas, preserved in stellar abundances, waiting for James Webb to decode. Like dinosaur fossils revealing prehistoric life, chemical fossils reveal prehistoric stars, extinct species that once dominated their era, giants that shaped cosmic evolution before vanishing completely. Monster stars would have been spectacular while they lived, blazing thousands of times brighter than normal stars, outshining entire regions of their host galaxies. pumping out ultraviolet radiation, ionizing surrounding gas, creating bubble-like structures in the cosmic web. Their brief lives would have been violent. Stellar winds carrying mass outward, pulsations shaking the entire star, occasional eruptions ejecting material, the whole object barely stable, constantly fighting gravitational collapse. When they finally collapsed, they would disappear almost instantly. The event horizon forms. The singularity emerges. The star ceases to exist in normal spacetime, leaves only a black hole and a chemical signature. Those black holes remain today, grown larger through mergers and accretion, hidden inside galactic centers, contributing to the supermassive monsters James Webb observes throughout the early universe. Monster stars, dinosaurs of the cosmic past, enormous, primitive, gone forever. But their legacy remains written in starlight. 570 million years after the Big Bang, a black hole feeds. The object sits in galaxy CANUCS LRDZ 8.6, confirmed by James Webb spectroscopy, actively growing, consuming gas from its surroundings, shining as it feeds. This black hole exists when the universe is barely breathing. The timing creates problems. Black holes grow from smaller seeds. Stellar mass black holes form from dying stars. These merge together, gradually build mass, eventually reach supermassive status. The process takes time, hundreds of millions of years minimum, often billions. CANUCSLRDZ 8.6 contains a supermassive black hole at 570 million years post-Big Bang. The timeline doesn't work. Not enough time has passed for normal growth processes. Yet the black hole exists, massive, active, feeding. Nicholas Martis analyzed the spectroscopy data, University of Ljubljana researcher. His description highlighted the key problem. The spectral features revealed by Webb provided clear signs of an accreting black hole at the center of the galaxy. The data shows active feeding, matter spiraling inward, energy pouring outward. The black hole is overmassive compared to its host galaxy. Normally, supermassive black holes correlate with galaxy mass. Bigger galaxies host bigger black holes. The relationship is tight, well established. CANUCSLRDZ 8.6 breaks this rule. The black hole weighs too much for the galaxy hosting it, grew too large too fast, dominated the system before the galaxy could catch up. This suggests black holes grew faster than their host galaxies in the early universe, a reversal of modern relationships. This discovery connects to little red dots. The galaxy belongs to that mysterious population, small, red, compact, harboring active black holes. James Webb finds them throughout the early universe, each one challenging our understanding of black hole growth. The black hole's feeding process releases energy, massive amounts. This energy influences the surrounding galaxy, heats gas, drives winds, suppresses star formation in some regions, triggers it in others. The black hole shapes galactic evolution through feedback. Understanding this feedback matters for cosmology. Black holes and galaxies co-evolve. Each influences the other's growth. Getting the relationship wrong means misunderstanding galaxy formation. Getting the timeline wrong means misunderstanding cosmic evolution. CANUCSLRDZ 8.6 represents one example among many. James Webb has confirmed multiple early supermassive black holes. Each observation adds to the puzzle. Each discovery demands explanation. The pattern is clear. Black holes appeared earlier and grew faster than theories predicted. Several explanations exist. First, seed black holes might have been more massive than we thought. If they started heavier, they reached supermassive status faster. But where did heavy seed black holes come from? Direct collapse of gas clouds? Monster stars? Something else? Second, feeding rates might have been higher in the early universe. more gas available, less regulation from feedback. Black holes could gorge themselves, accumulate mass quickly, reach enormous sizes in short times. This requires different conditions than modern universe provides. Third, black hole mergers might have happened more frequently. Galaxies collided constantly in the crowded early universe. Their black holes merged, combined masses, grew rapidly through cannibalism. This process accelerates growth beyond normal accretion rates. All three mechanisms probably contributed. The early universe provided perfect conditions for rapid black hole growth: dense environments, abundant gas, frequent mergers. Black holes exploited these conditions, grew to supermassive status in cosmic minutes. The research team plans additional observations, studying cold gas and dust around the black hole, measuring exact properties, determining feeding rates, building detailed models of early black hole growth. The goal is understanding how black holes and galaxies co-evolved in the first billion years. This epoch set the stage for everything that followed. The structures formed then influenced galactic evolution for the rest of cosmic history. CANUCSLRDZ 8.6 shines across 13 billion light-years, a black hole feeding in the infant cosmos, growing impossibly fast, dominating its host galaxy, challenging every theory we built about black hole formation. James Webb watches it feast, records every detail, collects data that will reshape our understanding of cosmic dawn. The black hole keeps feeding, keeps growing, keeps defying our expectations. 740 million years after the Big Bang, two galaxies collide. Their black holes prepare to merge. The system is called ZS7. Discovered by James Webb in the extreme early universe, two massive black holes orbit each other, spiral inward, approaching merger. This represents the most distant black hole merger ever detected, the first confirmed in such ancient times. Hannah Ubler leads the research team, University of Cambridge astronomer. Her description emphasizes what spectroscopy revealed. We found evidence for very dense gas with fast motions in the vicinity of the black hole, as well as hot and highly ionized gas illuminated by the energetic radiation. The signatures are clear: two black holes, both active, both preparing to collide. Black hole mergers release gravitational waves, ripples in space-time itself. These waves propagate outward at light speed, carry information about the merging objects. Observatories on Earth detect them as tiny vibrations. The merger in ZS7 happened too long ago for current detectors. The gravitational waves already passed Earth billions of years before our planet existed. Future detectors might catch similar events. The Laser Interferometer space antenna will launch in the coming decades. This space-based observatory will detect gravitational waves from supermassive black hole mergers. Events like ZS7, but happening in our cosmic era. The waves will reveal merger dynamics, black hole masses, orbital parameters. The ZS7 merger challenges formation theories. Two supermassive black holes existed 740 million years post-Big Bang, each one massive enough to dominate its host galaxy. Both black holes had to grow rapidly before the galaxies collided. This requires even faster growth rates than single early black holes demand. The merger itself accelerates growth. When black holes combine, their masses add. 2 million solar mass black holes become 1/4 million solar mass black hole. The process bypasses slow accretion, provides instant mass increase. Multiple mergers could build supermassive black holes quickly. This mechanism might explain early supermassive black holes. They didn't grow from single seeds through gradual feeding. Instead, many smaller black holes merged repeatedly. Each collision doubled mass. After enough mergers, supermassive status was reached. The crowded early universe provided perfect conditions: frequent galaxy collisions, frequent black hole mergers, rapid growth. Pablo Pérez González contributed to the study. The Centro de Astrobiología researcher offered perspective. The stellar mass of the system we studied is similar to that of our neighbor, the Large Magellanic Cloud, a small galaxy by modern standards, yet hosting not one but two supermassive black holes. The contrast is striking. The Large Magellanic Cloud orbits the Milky Way, contains perhaps 10 billion stars, relatively modest mass. Imagine it hosting two supermassive black holes, each one as massive or larger than Sagittarius A star. The galaxy would be dominated by its black holes. Stellar populations would play supporting roles. ZS7 operates under those conditions. Black holes rule. Stars serve as background players. The galaxy exists primarily as fuel for its central monsters. When the black holes finally merge, the event will be catastrophic. Gravitational waves will ripple through space-time. Energy equivalent to millions of stellar explosions will release in seconds. The merged black hole will recoil, possibly kicked out of the galaxy entirely, racing through space as a rogue monster. Or the merged black hole might remain, settling into the galactic center, continuing to feed, growing even larger, eventually becoming the kind of supermassive black hole we observe in modern galaxy cores. The merger also affects the host galaxies. Gas gets shocked. Star formation triggers in some regions, quenches in others. The galaxies themselves might merge into one, their stellar populations mixing, creating a new, larger galaxy. This galaxy will bear the scars of its violent birth: disturbed structure, unusual stellar orbits, signs of past trauma. Hubler summarized the implications. Our findings suggest that merging is an important route through which black holes can rapidly grow, even at cosmic dawn. The early universe assembled its structures through collisions. Galaxies merged, black holes merged, everything crashed together in cosmic chaos. Modern universe appears calmer. Space has expanded. Galaxies spread apart. Collisions are rarer. The frenzied merger epoch ended billions of years ago, but its legacy remains. The supermassive black holes in modern galaxies, the elliptical galaxies born from mergers, the metal-enriched gas clouds, all products of ancient violence. ZS7 captures that violence in action. Two black holes spiraling toward destruction, two galaxies colliding, one future system emerging from primordial chaos. James Webb recorded the event frozen in time, light that left ZS7 13 billion years ago, showing us what the early universe really looked like: violent, chaotic, merging. The collision continues in real time, 13 billion light-years away. The black holes have long since merged. The new system exists today, but we see only the past, the frozen moment captured by ancient light. A supermassive black hole races through space at 2.2 million miles per hour. The object is confirmed by James Webb, a runaway monster ejected from its home galaxy, fleeing through the cosmos like a cannonball fired from gravitational chaos. This represents the first confirmed runaway supermassive black hole ever observed. The velocity is staggering. 2.2 million miles per hour equals roughly 1,000 kilometers per second, 1/3 of 1% the speed of light. Fast enough to cross the distance between Earth and our nearest stellar neighbor in just 4 years. Absurdly fast for an object millions of times more massive than our star. What force could launch a supermassive black hole like a bullet? Galaxy mergers provide the answer. When two galaxies collide, their central black holes eventually meet. They spiral toward each other, orbit, eventually merge. The merger releases gravitational waves. These waves carry momentum. If the waves emit asymmetrically, they push the merged black hole in one direction, a gravitational rocket engine. The push can be powerful, strong enough to eject the black hole entirely, launch it out of the galaxy at millions of miles per hour, send it wandering through intergalactic space. This is called a gravitational wave recoil kick. The runaway black hole leaves evidence behind. As it tears through space, it plows through gas, compresses it, heats it, triggers star formation in its wake, creates a trail of young stars marking its path, a contrail through the cosmos. James Webb detected this contrail, a stream of stellar nurseries following the black hole's trajectory. Each nursery glows with infant stars, hot, blue, recently ignited. The trail points back toward the black hole's former home, traces its escape route across millions of light years. The discovery boggles minds. A black hole massive enough to dominate a galaxy, traveling fast enough to escape gravitational bonds, leaving a wake of star formation across intergalactic void. The scenario sounds like science fiction. James Webb proved its science fact. The black hole continues traveling, will wander through darkness for billions of years. Eventually, it might encounter another galaxy, fall inward under gravity, settle into a new home, resume feeding. But for now, it travels alone, a rogue monster racing through empty space. The contrail will fade, the young stars will age, cool, eventually die. The evidence of the black hole's passage will disappear. Future astronomers billions of years from now might never know a runaway monster once tore through their cosmic neighborhood. Similar runaways probably exist throughout the universe. Most travel through empty regions where little gas exists. They create no trails, leave no evidence. Invisible wanderers. James Webb caught one by luck. It happened to plow through a gas-rich region, created a visible wake, announced its presence. How many runaway black holes haunt the cosmos? Dozens? Thousands? Millions? Nobody knows. They're nearly impossible to detect unless they interact with something. Most probably wander in darkness forever, invisible exiles from galactic homes they can never reclaim. The gravitational wave kick required precise conditions. The merging black holes must have had unequal masses, must have been spinning at specific rates, must have approached from particular angles. Everything needed to align perfectly. When it did, the kick launched the merged black hole into space. Future gravitational wave observatories will detect these mergers as they happen, measure the kick strengths, determine how common runaway black holes really are. For now, James Webb provides glimpses, individual cases, proof the phenomenon exists. The runaway travels onward, fleeing its past, racing toward an uncertain future, a supermassive exile, hurtling through the void at 2.2 million miles per hour. And somewhere in its wake, stars ignite, born from the passage of a cosmic monster, marking the trail of the impossible. A scar stretches across galaxy NGC 3627, 20,000 light-years long, 650 light-years wide, a contrail carved by something massive plowing through space. This represents the clearest galactic contrail ever discovered. Previous examples existed in the Milky Way, small, ambiguous, difficult to interpret. NGC 3627 scar is unmistakable, enormous, well-defined, impossible to miss. Menke Zhao discovered it, a doctoral student at Nanjing University in China. The discovery came while analyzing survey data, images from multiple telescopes, including James Webb. The contrail appeared as an unusual linear structure, too narrow, too long, too strange to be natural galactic features. Something carved this path through the galaxy. Two possibilities exist. First, a supermassive black hole, ejected from the galactic center, plowing outward through gas and dust, compressing material as it travels, triggering star formation in its wake. The contrail marks its escape route. Second, a dwarf galaxy, colliding with NGC 3627, passing through at high speed, its gravity disturbing gas, creating compression waves, sparking stellar birth along its trajectory. The contrail marks the collision path. Both scenarios are dramatic. Both require violent events. Both leave permanent scars on the host galaxy. Zhao cannot yet distinguish between them with available data. Currently, with the available data, we cannot definitively distinguish between these two possibilities. More observations are needed. The contrail's dimensions are remarkable. 20,000 light-years equals 1/5 the diameter of the Milky Way. Imagine a scar that long carved through our galaxy, stretching from the galactic center beyond the outer spiral arms, visible from billions of light-years away, a permanent wound in galactic structure. The width is narrow by comparison, only 650 light-years. This creates an aspect ratio similar to a pencil line, long, thin, precise. The object that created it followed a straight trajectory, plowed through without deviation, left a laser-straight scar. Star formation lines the entire contrail. Young stellar clusters, hot blue stars, glowing nebulae. The compression wave triggered intense stellar birth. Gas that might have taken millions of years to collapse was shocked into rapid formation. Stars ignited in cosmic minutes instead of cosmic eons. The energy required to create this scar is staggering. Whether a black hole or dwarf galaxy, the object carried immense momentum, crashed through galactic gas at tremendous speed, left this 20,000 light-year wound as evidence of its passage. NGC 3627 will bear this scar forever. The contrail will fade as stars age and die, but the structural disturbance remains permanent. The gas has been rearranged, the galactic disk forever altered. Future astronomers studying this galaxy will see evidence of ancient violence. Similar contrails might exist throughout the universe. Most would be too faint to detect, too distant to resolve, too old to show active star formation. NGC 3627's contrail is fresh, active, blazing with newborn stars. This makes it detectable across cosmic distances. The discovery came from combining multiple datasets, ground-based telescopes, space telescopes, different wavelengths, different instruments. Only by synthesizing all available data did the contrail emerge. Single observations would have missed it. The lesson is clear. Comprehensive surveys reveal what focused studies cannot. Zhao's team suggested another possibility. Little red dots might create similar features, those mysterious early universe objects. If they plow through galaxies, they might leave contrails, but the mechanism remains unclear. Little red dots are compact. How they would create 20,000 light-year scars is unknown. Future observations will determine what created NGC 3627's scar. Deep optical surveys might reveal a faint dwarf galaxy. High-resolution observations might pinpoint a runaway black hole. Spectroscopy might measure velocities and compositions. The truth will emerge with more data. For now, the scar remains. A 20,000 light-year wound, evidence of cosmic violence, proof that galaxies suffer injuries that never fully heal. Something massive tore through NGC 3627, left destruction in its wake, carved a permanent reminder of its passage, and moved on. The scar glows with young stars, marks of trauma transformed into stellar nurseries, beauty born from violence, life emerging from destruction. James Webb captured it in unprecedented detail, revealed the contrail's full extent, showed us what happens when cosmic monsters rampage through galaxies. James Webb peered beyond the Milky Way, found objects that shouldn't exist there. The target was NGC 602, a young star cluster in the Small Magellanic Cloud, our galactic neighbor, roughly 200,000 light-years away, close enough for detailed study, far enough to be outside our galaxy's influence. Among the bright young stars, astronomers spotted something strange. Dozens of objects too faint to be stars, too bright to be planets. Brown dwarfs, failed stars, objects that tried to become stars but didn't accumulate enough mass. This marks the first potential brown dwarf detection beyond the Milky Way. Previous discoveries all occurred within our galaxy. Finding them in another galaxy changes everything we know about their formation and distribution. Brown dwarfs occupy a strange category, more massive than giant planets like Jupiter. not massive enough to sustain hydrogen fusion. They ignite briefly, burning deuterium, then fade, cooling slowly over billions of years, radiating leftover heat into darkness. The mass threshold sits around 75 times Jupiter's mass. Above that, objects become stars. Below that, they remain brown dwarfs, forever, doomed to cool, never achieving true stellar status. Failed attempts at becoming cosmic engines. Why finding them in the Small Magellanic Cloud matters comes down to metallicity. The Small Magellanic Cloud contains fewer heavy elements than the Milky Way. Less iron, less carbon, less oxygen. The gas is more pristine, closer to the early universe's composition. Previous theories suggested brown dwarfs form more easily in metal-rich environments. Heavy elements help gas cool. Cooling aids fragmentation. Fragmentation creates smaller clumps. These clumps might become brown dwarfs instead of stars. The Small Magellanic Cloud's low metallicity should make brown dwarf formation harder. Yet, there they are, dozens of brown dwarf candidates, forming in conditions that should suppress them. The discovery demands explanation. Elena Sabi investigates these objects. National Science Foundation's NOIRLL researcher. Her team used James Webb's infrared capabilities to detect the faint brown dwarf candidates. Previous telescopes lacked sensitivity, could not distinguish brown dwarfs from background objects at these distances. The brown dwarfs in NGC 602 are young, recently formed, still glowing with heat from their rapid contraction. This makes them brighter and easier to detect. Older brown dwarfs would fade into invisibility. Even James Webb would struggle to find them. If confirmed, these detections reveal that brown dwarf formation is more universal than thought. Occurs across different environments, different metallicities, different galactic conditions. The process is robust, adaptable, common throughout the cosmos. The implications extend to planet formation. Brown dwarfs and giant planets occupy adjacent mass ranges. Understanding how brown dwarfs form informs theories of giant planet formation. If brown dwarfs form easily everywhere, giant planets probably do too. This matters for searching for life. More giant planets means more potential systems like our own. More gas giants protecting inner rocky worlds from asteroid bombardment. More gravitational anchors stabilizing planetary systems. More opportunities for life-friendly conditions. The Small Magellanic Cloud offers other advantages for studying star formation. Its lower metallicity resembles the early universe. Observing star formation there provides insights into how the first stars and planets formed when heavy elements were scarce. When conditions were primitive, NGC 602 contains approximately 5,000 stars, young, hot, massive, born within the last few million years, a stellar nursery in full bloom. The brown dwarf candidates hide among these bright stars, faint companions to their successful stellar siblings. Confirmation requires additional observations. Spectroscopy will measure temperatures, compositions, surface gravities. These measurements distinguish brown dwarfs from low-mass stars or background galaxies. The process takes time, telescope time, analysis time, years before final answers emerge. For now, the candidates remain candidates, probable brown dwarfs, likely failed stars, first of their kind found beyond our galactic borders. Proof that these objects exist throughout the universe, not just in our cosmic backyard. The failed stars hide in plain sight, too faint for most telescopes, too common to be exotic, too strange to fully understand. James Webb revealed them anyway, and changed our understanding of where these objects can form. 330 million years after the Big Bang, a galaxy shines through fog. The object is JADES GSZ 131, confirmed by James Webb spectroscopy, emitting bright hydrogen emission called Lyman alpha. This should be impossible. The early universe was filled with neutral hydrogen fog. This fog absorbs Lyman alpha emission completely. No galaxy should shine through it alone. Yet JADESGSZ 13.1 blazes anyway. The early universe went through an era called reionization. Neutral hydrogen atoms filled space. This fog blocked ultraviolet light, made the cosmos opaque. Eventually, the first stars and galaxies produced enough radiation to ionize the hydrogen, strip electrons from atoms, clear the fog, create transparent space. This process took hundreds of millions of years, many galaxies contributing, countless stars pumping out ultraviolet photons, slowly burning through the cosmic fog. The effort was collective. No single galaxy could clear the fog alone. JADESGSZ 13.1 exists before reionization finished. The fog still dominated, yet its Lyman alpha emission reaches us, travels 13 billion light-years, arrives at James Webb's instruments, clear, bright, unabsorbed. Joris Wittstock leads the research team, University of Cambridge and University of Copenhagen astronomer. His description emphasizes what spectroscopy revealed. The galaxy shows dense gas with fast motions near its core. Hot ionized gas, illuminated by energetic radiation, all signatures of intense activity. The galaxy must be creating a bubble, a region around itself where hydrogen is ionized, cleared of fog, transparent to Lyman alpha emission. The bubble allows light to escape, travel through reionization-era space, reach our telescopes billions of years later. Creating such a bubble, single-handedly, requires immense power. The galaxy must produce tremendous amounts of ultraviolet radiation, enough to ionize hydrogen across light-years. Maintain the bubble against the surrounding fog. Keep it clear continuously. This demands extreme star formation rates, or an active supermassive black hole, or both. The galaxy operates at maximum output, blazing at the edge of what physics allows, pumping out enough energy to clear its cosmic neighborhood. The discovery changes our understanding of reionization. Previous models assumed collective effort, many galaxies working together, each one contributing small amounts of ionizing radiation, together clearing the fog gradually over hundreds of millions of years. JADESGS Z13.1 suggests individual galaxies played larger roles, powerful enough to clear substantial bubbles. These bubbles would grow, eventually merge, create the transparent universe we see today. Fewer galaxies needed, each one more powerful. This resolves a puzzle. James Webb finds fewer galaxies in the early universe than predicted. If reionization required countless small galaxies, the numbers don't work. Not enough galaxies exist to produce the necessary ionizing radiation. But if individual galaxies are much more powerful, fewer are needed. JADESGS Z 13.1 provides proof. One galaxy, one bubble, enough power to clear its surroundings. This model works mathematically, explains observations, resolves the galaxy count problem. The bright Lyman alpha emission also teaches us about early galaxy properties. The emission traces hydrogen gas, shows where it's densest, where it's moving, how it's distributed. This maps the galaxy's structure, reveals details invisible through other observations. The fast gas motions indicate turbulence, materials swirling violently, possibly driven by stellar winds, supernova explosions, black hole feedback. The galaxy is chaotic, energetic, violent. Not a calm stellar nursery, but a cosmic storm. Before and during reionization, neutral hydrogen fog blocked ultraviolet light, like colored glass filtering certain wavelengths. Until enough stars formed and ionized the hydrogen, no energetic light could escape early galaxies. No Lyman alpha emission could reach Earth. JADESGS Z 13.1 shouldn't be visible. The fog should hide it, absorb its light, make it invisible to our instruments. The galaxy defies this, shines through, announces its presence. The team describes it as mysteriously clearing fog, creating transparency where none should exist, operating with power levels that seem impossible for such an early time. The universe at 330 million years post-Big Bang was hostile, dark, foggy, opaque. Galaxies struggled to form, fought against cosmic conditions. Most remained invisible behind the hydrogen veil. JADESG, S said. 13.1 burned through the veil, cleared the fog, made itself visible. A beacon in the cosmic dark ages. Proof that individual galaxies could reshape their environments. James Webb detected the light, confirmed the impossible, showed us what one galaxy could accomplish alone. Gather all the observations together. Notice the pattern. Galaxies form faster than theories predict. Black holes grow faster than models allow. Stars assemble faster than physics should permit. Everything in the early universe operates in fast forward. The cosmic film plays at double speed. Standard galaxy formation proceeds slowly. Gas collapses under gravity, forms small clumps. These clumps merge, create larger structures. The process repeats. Over billions of years, galaxies reach maturity, develop spiral arms, build massive stellar populations, achieve the structures we observe today. This timeline worked perfectly, matched computer simulations, explained observations from Hubble, provided a coherent picture of cosmic evolution. Then James Webb looked deeper, found mature galaxies existing when they should barely be forming. The timeline shattered. Alaknanda, assembled in a few 100 million years, built 10 billion stellar masses, developed perfect spiral structure, accomplished in 1/10 the time what should require billions of years. The galaxy formed in fast forward. Zhulong appeared fully developed 1 billion years post-Big Bang. Spiral arms, central bulge, organized disk, all features requiring extended formation times, all present impossibly early. Another galaxy skipping ahead through time. The massive red galaxies contain aged stars, stars that lived billions of years, existing in a universe only hundreds of millions of years old. The math doesn't work. The observations remain solid. Supermassive black holes appear 500 million years after the Big Bang, already dominating their host galaxies, already feeding actively, growing from unknown seeds at impossible rates, racing toward supermassive status in cosmic minutes. Star formation rates in early galaxies exceed modern examples by factors of 20 or more. Gas converts to stars with extreme efficiency, building stellar populations at speeds standard models cannot explain. The stellar assembly line runs at maximum speed. Every observation points the same direction. The early universe was more efficient than the modern cosmos. Assembled structures faster, organized matter more quickly, achieved in millions of years what now requires billions. Why? Several factors might contribute. Gas in the early universe was denser, galaxies crowded closer together, gravitational interactions were stronger. These conditions could accelerate all processes, make formation faster, enable the rapid assembly James Webb observes. The early universe also lacked heavy elements. Pristine hydrogen and helium dominated. This changes cooling rates, affects how gas fragments, might allow larger structures to form directly, skip intermediate steps, reach maturity faster. Dark matter might behave differently than simulations predict. Perhaps it clumped more efficiently early on, provided stronger gravitational wells, allowed normal matter to fall in faster, accelerated galaxy formation beyond what models calculate. Or maybe our understanding of star formation is wrong. Perhaps the relationship between gas and stars differs in the early universe. Higher efficiency, different mass distributions, processes that no longer operate in the modern cosmos. The pattern appears across all observations, not limited to one type of object, not confined to one cosmic era. Everything forms faster, everything grows quicker. The entire early universe operates at accelerated pace. This demands theoretical revision. Galaxy formation models need adjustment. Star formation physics requires updates. Black hole growth timelines must be rewritten. The standard framework needs modification throughout. Some astronomers suggested more radical changes. Perhaps the standard model of cosmology is wrong. Maybe dark energy behaves differently than assumed. Maybe the expansion rate varied more than calculated. These changes would ripple through all cosmic timelines. Most prefer conservative solutions. Adjust parameters within existing frameworks. Tweak star formation efficiency. Modify merger rates. Increase gas density. Small changes that preserve the overall picture while matching observations. But small changes might not be enough. James Webb keeps finding galaxies that push boundaries further. Each observation demands more adjustment, more parameter tweaking, more special pleading. Eventually, the framework might collapse under accumulated modifications. The early universe assembled in fast forward. This is observational fact. Explaining how requires theoretical innovation, either within existing frameworks or through revolutionary new models. James Webb provides the observations, shows us what really happened. Now theorists must explain it. The cosmic film plays at double speed, and nobody knows how to slow it down to match expectations. Delicate structures persist through chaos. This shouldn't happen. Spiral arms are fragile, density waves propagating through galactic disks, maintained by precise gravitational choreography, disrupted easily by external perturbations. Major galaxy mergers destroy them instantly. The mathematics is clear. Collisions smear spiral structure into featureless ellipticals. The early universe was collision-heavy. Galaxies crowded together. Mergers happened constantly. Dwarf galaxies smashing into each other. Larger galaxies cannibalizing smaller ones. Violence dominated cosmic evolution. Spiral structures had no business surviving. Yet over 1,600 spiral galaxies exist in the early universe. Delicate arms, perfect symmetry, undisturbed structure. They survived the collision epoch, maintained organization through chaos. One example is particularly remarkable, mentioned briefly in research about early disk galaxies, a spiral galaxy in a busy, crowded region of space. Location suggests it experienced collisions or mergers. Yet the spiral structure remains pristine. The arms show no disruption, no evidence of recent violence. Standard merger models predict destruction. When two galaxies collide, tidal forces stretch spiral arms. Gravitational interactions twist them. The delicate density waves dissipate. Stars scatter into broader distributions. The result is an elliptical galaxy, featureless, lacking structure. This happens in the modern universe. We observe elliptical galaxies. Know they formed from mergers. Can simulate the process in computers. Watch spiral galaxies collide. See the arms destroyed. Witness elliptical formation. The physics works perfectly for modern collisions. Early universe collisions should be worse. Higher velocities, more frequent encounters, stronger perturbations. Spiral arms should be even more vulnerable, yet they survive. Possible explanations exist, but none fully satisfy. Perhaps early spiral galaxies were more robust, denser stellar disks, stronger self-gravity, better able to resist tidal disruption. This requires different galaxy properties than models predict. Maybe mergers occurred at particular angles. Head-on collisions destroy structure. Glancing impacts might preserve it. If most early mergers were glancing rather than direct, spiral arms could survive. But this requires unlikely coincidence across hundreds of galaxies. The gas content might matter. Early galaxies contained more gas. Gas damps disturbances. Help structures reform after perturbations. Even if spiral arms get disrupted, gas infall could restore them quickly. The galaxy heals itself after violence. Or perhaps spiral structure forms faster than we think, gets destroyed in mergers, reforms within millions of years. appears pristine in observations despite recent violence. This requires extremely efficient spiral arm formation, faster than current models allow. Each explanation has problems. Each requires adjusting some aspect of galaxy physics. Together they suggest our understanding of galaxy dynamics is incomplete, missing some process, some stabilizing mechanism, some factor that makes spiral structure more resilient than predicted. The 1,000+ early spiral galaxies demand explanation. They're not outliers, not rare exceptions. They're common, numerous, representing a significant fraction of all early galaxies. The phenomenon is widespread. This abundance suggests spiral galaxies dominated the early universe more than the modern cosmos. Today, ellipticals are common, products of billions of years of mergers. In the early universe, spirals prevailed. Despite living through the most violent epoch of cosmic history, the survival of spiral structure matters for understanding galactic evolution. If delicate features persist through chaos, galaxies are more stable than we thought, less affected by their environments, more able to maintain organization despite disturbances. This has implications for planet formation. Spiral density waves trigger star formation. Stars form with planetary systems. Stable spiral structure means consistent star formation. Consistent star formation means more planets. More planets means more opportunities for life. If spiral galaxies dominated the early universe, life might have started earlier than we thought, in stable galactic environments, protected by persistent structure, developing while the cosmos was young. The delicate spiral arms survive, persist through violence, maintain beauty through chaos, defy expectations, challenge theories. James Webb captured them in detail, showed their perfection, revealed their impossible resilience. And astronomers struggle to explain how such fragile structures endure. Star formation follows rules. Gas collapses, heats, fragments, forms stars of various masses. The mass distribution follows a pattern called the initial mass function. Most stars are small, few are massive. The ratio is predictable, universal, observed everywhere we look until James Webb looked at the early universe. Star formation, there might follow different rules, create different mass distributions, produce stellar populations unlike anything in the modern cosmos. The cosmic blueprint doesn't apply to the infant universe. Evidence comes from multiple sources. The unusually bright early galaxies, too bright for standard stellar populations. Either they contain more stars than estimated, or the stars shine brighter than expected. Different mass distributions could explain both. If early stars skewed more massive, they would shine brighter. A galaxy with many massive stars outshines one with typical distributions. This could explain why early galaxies blaze so brightly, not more stars. Different stars. Massive stars live fast, die young, explode as supernovae, enrich the cosmos with heavy elements. A top-heavy initial mass function would produce more supernovae, more heavy element production, faster chemical evolution. This might explain why some early galaxies show unexpected metal abundances. The monster star evidence supports this. GS3073's chemical signature suggests extremely massive stars, 10,000 solar masses. These titans would shift the initial mass function dramatically toward high masses, create stellar populations dominated by giants. Why would early star formation differ? Conditions provide the answer. The early universe lacked heavy elements. Pristine gas collapses differently than metal-enriched gas. Cooling proceeds at different rates. Fragmentation follows different patterns. This could shift the initial mass function. Radiation fields were stronger in the early universe, more energetic photons. These photons heat gas. Heating prevents small fragments from collapsing. Only larger clumps survive. Larger clumps form more massive stars. The harsh radiation environment favors giants over dwarfs. gas density was higher. Denser gas means stronger gravity. Stronger gravity means faster collapse. Faster collapse means less fragmentation. Less fragmentation means fewer small stars, more massive ones. The dense conditions favor top-heavy distributions. All these factors combined could dramatically alter star formation, create populations unlike anything observed today, produce the unusual properties James Webb detects in early galaxies. This has profound implications. If star formation operated differently in the early universe, we cannot use modern observations to understand cosmic dawn. The processes were fundamentally different. Extrapolating backward fails. Chemical evolution accelerates with top-heavy initial mass functions. More massive stars means more supernovae. More supernovae means faster heavy element production. Galaxies would reach metal-rich states faster. This might explain why some early galaxies appear surprisingly mature chemically. Planet formation might also differ. Massive stars produce different conditions around them, different radiation environments, different heavy element distributions. Planets forming near massive stars would experience different circumstances than modern planetary systems. The different initial mass function might be temporary. As the universe aged, conditions changed. Heavy elements accumulated. Radiation fields weakened. Gas density dropped. Star formation gradually shifted toward modern distributions. Today's initial mass function emerged over cosmic time. This means there's a transition period, an era when star formation shifted from early top-heavy distributions to modern patterns. Finding this transition would pin down when and how the shift occurred. James Webb might already have data showing this transition, buried in observations awaiting analysis. Understanding early star formation requires abandoning assumptions based on modern observations. The rules were different, the physics was different, the outcomes were different. We cannot assume universality. Stars formed without following the modern blueprint, created populations we don't see locally, operated under conditions that no longer exist, produced the strange properties James Webb observes throughout the early universe. The cosmic blueprint was still being written. Star formation was experimental, trying different approaches, eventually settling on the patterns we observe today. But in the beginning, the rules were different, and the stars that formed reflected those different rules. Dark matter holds the universe together. Invisible scaffolding, 5 times more abundant than normal matter, provides gravitational wells for galaxies to form within. Essential to cosmic structure. The theory is solid. Observations confirm it. Simulations require it. James Webb finds galaxies that shouldn't exist without dark matter, formed too early, too massive, too organized. The dark matter structures weren't ready yet. The timing doesn't work. The scaffolding wasn't in place. ZFUDS 7329 exemplifies the problem. Massive galaxy, 800 million years post-Big Bang. Dark matter halos that size shouldn't exist yet. They need more time to grow. The galaxy formed anyway. This pattern repeats. Early massive galaxies throughout James Webb observations, each one demanding dark matter structures that weren't ready, each one existing despite theoretical impossibility. The evidence accumulates. 3 possibilities emerge. First, dark matter clumps faster than simulations predict. Perhaps it interacts with itself. Self-interaction could accelerate clumping, create halos earlier than non-interacting models allow. This preserves dark matter while adjusting its properties. Second, the initial density fluctuations were larger than assumed, bigger primordial seeds. These would grow faster, reach galaxy hosting size earlier, allow early galaxy formation. This preserves the growth model while adjusting initial conditions. Third, dark matter doesn't provide the scaffolding we think it does. Galaxies can form without it, or with less of it, or following different mechanisms entirely. This possibility terrifies cosmologists. Dark matter is foundational. Removing it collapses modern cosmology. Most astronomers prefer the first two options: adjustments within the dark matter paradigm, modified properties, or modified initial conditions. Both preserve the overall framework while matching observations. But adjustment has limits. Each new observation requires more tweaking, more parameter modification, more special conditions. Eventually, the accumulated adjustments become implausible. The model becomes contrived. Some researchers suggest alternative gravity theories, modified Newtonian dynamics, other approaches that eliminate dark matter entirely, explain galactic dynamics through gravitational modifications instead of invisible mass. These theories struggle with other observations: cosmic microwave background, large-scale structure, gravitational lensing. The early galaxy problem isn't the only dark matter challenge. Other observations create tension: the core cusp problem, the missing satellites problem, the too big to fail problem. Dark matter simulations predict things we don't observe, don't predict things we do observe. Each problem admits individual solutions: adjust star formation feedback, modify halo properties, invoke environmental effects. Taken together, the solutions become complex: many moving parts, many free parameters. The simplicity that made dark matter attractive fades. James Webb observations intensify the pressure. Each impossible early galaxy adds weight. Each overmassive black hole piles on. The evidence mounts. Something is wrong with our understanding. Whether that something is dark matter properties, initial conditions, galaxy formation, physics, or something more fundamental remains unclear. The observations demand explanation. The theories struggle to provide it. Dark matter's grip on cosmic structure weakens. Not gone, not disproven, but loosened. Less certain, more questioned. The invisible scaffolding might need reconstruction or replacement. The universe assembled faster than dark matter should allow. Galaxies formed before halos were ready. Black holes grew before seeds could build. Everything happened too quickly for the standard dark matter timeline. Either the timeline is wrong, or the role of dark matter is wrong. Either way, something fundamental needs revision. The observations won't go away. James Webb keeps finding more impossible galaxies, more early structures, more evidence that challenges dark matter orthodoxy. Cosmologists face uncomfortable questions, questions that threaten the foundation of modern cosmology, questions that demand answers beyond parameter adjustments and special pleading. Dark matter held the universe together in our theories. In observations, the universe assembled without waiting for dark matter's permission. The invisible scaffolding might be real, but it might not work the way we thought, might not control cosmic evolution as completely as models suggest, might play a different role than we assigned it. James Webb reveals the problems, shows us where theories fail, exposes the gaps in our understanding. Now, cosmologists must rebuild, modify, adjust, or possibly revolutionize. The data demands it. The impossible galaxies insist upon it. Dark matter's grip loosens, and we watch to see what happens when it lets go. Connect the discoveries, trace the implications, follow the thread to its end. Everything we know about cosmic evolution comes from observations and theories. The observations were limited: ground telescopes, Hubble's visible light view, partial pictures, incomplete data. We built theories around what we could see, assumed the rest followed similar patterns. James Webb sees more, deeper, clearer. The complete picture emerges, and it looks nothing like we expected. Galaxies formed faster than theories allowed. This means galactic evolution happened differently than we thought. The slow build-up we assumed never occurred. Early galaxies assembled quickly, reached maturity in cosmic minutes. This changes everything about understanding galaxy populations. Stars formed under different rules in the early universe, different mass distributions, different efficiencies, different populations. We cannot extrapolate modern star formation backward. The early cosmos operated differently. This means our understanding of chemical evolution needs revision. The production of heavy elements followed different timelines. Heavy elements are crucial: carbon, oxygen, nitrogen, iron, everything needed for planets, for life, for us. If these elements appeared faster than we thought, life could have started earlier, much earlier, billions of years before Earth formed. Consider the implications. Disk galaxies dominated the early universe. Stable structures, organized star formation, life-friendly environments. If these existed 10 billion years ago, civilizations might have risen when our galaxy was barely forming. Entire cosmic histories could have played out before our solar system existed. This changes the Drake equation, the calculation estimating intelligent civilizations in the galaxy. One factor is the age of suitable environments. We assumed galaxies needed billions of years to become stable, to accumulate heavy elements, to provide life-friendly conditions. James Webb shows stable, metal-rich galaxies existed impossibly early. More time means more opportunities, more planetary systems, more chances for life to emerge, more potential civilizations. The universe might be older in terms of biological history than cosmic history suggests. Life might have had 13 billion years to develop, not the 8 or 9 billion we assumed. Where are they? If civilizations arose billions of years ago, where are their traces? Why don't we see evidence of ancient intelligence? This intensifies the Fermi paradox, makes the silence more puzzling, more ominous. The rapid assembly of cosmic structures also affects cosmological models. Dark matter's role becomes uncertain. The expansion history might differ from calculations. The universe's age might need adjustment. Everything connects. Change one piece and others shift in response. Black holes appearing so early suggests they play larger roles in galactic evolution than we thought. Their feedback shapes star formation. Their mergers release energy. Their growth influences surrounding matter. Understanding galaxies requires understanding their central black holes from the earliest times. The different conditions in the early universe mean we cannot fully understand cosmic history from local observations. We must look back, study ancient galaxies directly, learn from observation rather than extrapolation. James Webb provides this capability, shows us what really happened rather than what we calculated should have happened. This affects how we think about our place in the cosmos. We exist in a universe that assembled differently than we believed, under rules that changed over cosmic time, in a galaxy that might be less special than we assumed, around a star that formed from material processed through cycles we didn't know occurred. The atoms in our bodies came from stars. Those stars came from earlier generations. Those earlier generations formed under different conditions than modern stars. The chemical path from Big Bang to biology is more complex than we knew, more interesting, more mysterious. James Webb's discoveries humble us, remind us how much we don't know, how many assumptions we made, how wrong we were about cosmic history. The telescope tears apart comfortable theories, forces us to rebuild understanding from observations rather than assumptions. This is how science progresses. Observations challenge theories. Theories adapt or get replaced. Understanding deepens. The process is painful, exciting, essential. What James Webb found in our galaxy and beyond changes everything. Not because the observations are pleasant, because they're true. The universe assembled its structures faster than we thought possible, operated under rules we didn't know, produced conditions we didn't predict. And somewhere in that turbulent cosmic past, the seeds of everything we are were planted, in galaxies forming impossibly fast, around stars burning under different rules, from elements forged in conditions we're only now beginning to understand. James Webb looked deep into our galaxy, looked deep into cosmic history, found terror, found beauty, found truth, found questions we didn't know to ask, and answers we weren't prepared to hear. The universe is stranger than we imagined. more violent, more beautiful, more mysterious. And we've only just begun to see it clearly. The discoveries continue. James Webb keeps watching, keeps recording, keeps revealing impossible truths. And we must face what it shows us, adjust our understanding, rebuild our theories, accept that everything we thought we knew about cosmic history needs revision. This is the beginning, not the end. The beginning of deeper understanding, the beginning of better questions, the beginning of knowing what we don't know. James Webb looked deep into our galaxy. What it found is terrifying. What it means is profound. What comes next is uncertain. But we will keep looking, keep learning, keep discovering, because now we know the universe has secrets, and we've finally built the instrument to reveal them.